Hello and welcome to the wolfSSL live webinar, Getting Started with wolfMQTT, presented by wolfSSL Senior Software Engineer Eric. My name is Shizuka and I'll be moderating this webinar. All attendees will be in listen-only mode. If you have any questions, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. I invite you to follow us on Twitter at wolfSSL as well as other socials. Also, feel free to email us if you have any additional questions. And now I'd like to give a brief company overview before we move to the technical presentation. Today, wolfSSL secure over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which are engineers. This progress is of course supported by a strong partner network that we are proud of. Since the beginning, our engineering team has developed several embedded security products, including Wolf Clipped with DO178 support, HIP certification, and a HIPS ready offering, MQTT up to the V5 specification, SSHB2, PPM 2.0, a secure bootloader known as Wolf Boot, as well as Java wrapper and JSSE support, and commercial support for Coral. All of these offerings are accompanied by through maintenance and support plan up to the 24/7 level. We also offer full service consulting. And now I would like to turn it over to Eric to talk about getting started with Wolf MQTT.
Excellent. Thank you, Shizuka. Hi, everyone. Thanks for attending our webinar. I'm Eric Blankenhorn. I'm an engineer here at wolfSSL, and I'll be discussing the basics of the MQTT protocol and how the wolfMQTT the client library can help secure your IoT network. We'll start with a discussion about the specific needs of the Internet of Things. That will take us to an overview of the MQTT protocol itself. Then we'll review the different specifications that are supported by the wolfMQTT client library. Next, we'll take a look at the architecture of the library, the integration of with wolfSSL, and a quick look at the configuration options and the build processes. That leads us to talk about the many rich client examples available alongside the core library. Next, we can look at some of the ideas we have for the roadmap of wolfMQTT. And lastly, we'll answer any questions that you might have about the protocol or wolfMQTT specifically. So the primary concern of many IoT projects is one of resource constraints. These devices might have tight power budgets or small memory availability, or they might be operating on networks that are either unreliable or expensive, each of which requires minimizing the amount of data transferred. The MQTT specification is free to use, which has greatly enhanced its popularity among developers of devices that number in the tens of billions. Since the protocol is easily scalable, industries across the spectrum have found it to be suitable for their application. Also key for developers is how friendly the API is. There are really only 8 primary functions in the wolfMQTT library needed to have a fully functioning client. So MQTT stands for Message Queuing Telemetry Transport, or MQ Telemetry Transport, depending on who you ask. It was designed specifically for lightweight embedded type systems, but it is scalable to allow for efficient large networks. Individual MQTT packets are very small, and publishing a sort message, including overhead, is in the tens of bytes. The publish and subscribe methodology allows publishers to send lots of small bits of data that are related to a topic. Then that data will be sent to the subscribers of the topic. This allows a loosely coupled system in which devices do not need to have the state knowledge of their peers to communicate with them. Through the use of gateways and bridge devices, the peers don't even need to exist on the same network topology. Even more important to the devices that may be powered off To conserve resources, messages can be stored and resent until the transmission is successful. So brokers are the central point of contact for all the MQTT devices. Brokers act as the directory of all connected clients, the index of all the topics, and the distributor of all the messages. So choose your broker wisely. The protocol specifically recommends using TLS to communicate securely. Devices that need to go offline to conserve power can use session resumption to quickly reestablish the connection. This level of protection adds overhead, but luckily we have the world's best TLS library available, wolfSSL, of course. So we're going to talk a little about quality of service. This is useful for defining a message's integrity. Things like network capability, tolerance for missing data, and tolerance for duplicate data are all considerations when choosing the quality of service level. When a client subscribes to a topic, a QoS level is specified. Likewise, when a client publishes to a topic, a QoS level is specified. The highest QoS level is determined by the party with the lowest QoS. In other words, client A can publish at QoS 1, but if the subscriber, client B, for instance, uses QoS 0, then the client B will only be sent a QoS 0 version of the message from the broker. Now, with QoS 0, the broker does not acknowledge receipt of the message, and the message is not stored or retransmitted by the sender. QoS 0 is best suited for a stable network or non-critical data. Imagine something like a rain gauge sensor that reports data every minute. So a couple of minutes of readings lost here and there is probably okay. With QoS 1, the sender stores the message until it receives a PUBAC, acknowledgement packet from the receiver. In this case, a message could be sent or delivered multiple times. This is suitable when data is critical. In other words, it must be delivered, but it's okay if duplicate data is received. Furthermore, network restrictions like bandwidth or cost might not allow for the full QoS 2 handshake, which we'll talk about in a second. Imagine like a blood pressure monitoring application that is sent reports from a sensor containing the timestamp and the BP reading of an astronaut. The application can ignore readings with the same timestamp, but all the readings have to be recorded. This would be a good candidate for QoS 1. So QoS 2 is the most thorough, but also the most costly. It takes 4 transactions for each published message to complete a delivery. QoS 2 should be used when the application cannot handle multiple messages. For example, a firmware delivery that would waste precious network bandwidth receiving a duplicate message, or perhaps require all the device's storage capacity to even receive the payload. The MQTT specification allows up to 256 megabytes of payload per message. However, the actual maximum payload is often limited by the broker. For example, the limit for AWS is 128 kilobytes, while Azure limits client to broker transfers to 256 kilobytes, and broker to client messages are limited to only 64 kilobytes. So again, choose your broker wisely. The last will and testament allows other clients to be informed when devices have lost their connection to the broker. During a normal session, a client would disconnect, indicating an intentional orderly shutdown. But if a broker loses the connection ungracefully, then the disconnected client can inform its peers using the last will and testament message. Also, as you can see, there are only 14 packet types for the version 3.11 protocol. Packet snippers like Wireshark are aware of MQTT traffic by the packet header. It can be very useful for a client application to send a single subscribe packet on initialization and be notified of messages from multiple topics. The term publish here refers only to the message type. A message that is published can be a client, that will be sent to the broker, or the broker then publish the message to all clients who subscribe to the message's topic. So messages can also be marked for retention to be stored on the broker. If the message is retained by the broker, then new clients will be sent that message when they're ready for the first subscribe. This can be useful for conveying messages like system state. So a little bit about the specifications supported by wolfMQTT. Version 3.11 is the successor to version 3.0. It's the only protocol version currently supported by Azure. AWS recently updated to allow version 5.0 also. Version 5 was completed in March of 2019. It adds support for properties to be sent along with the command packets. Properties are a simple way to add custom metadata in the form of key value pairs. These can be used, for instance, to describe the format of the payload data. Recovery from command failures can be complex, and new error messages from the broker can be used to help the client know what went wrong during a failed subscriber publish. Topic aliases allow integer representations of complex topic names. This can significantly reduce the bandwidth required for messages. Here's a little bit of trivia for you. What happened to version 4.0? Well, the connect packet defines the 8-bit unsigned protocol field, level field. So a value of hex 0 by 03 corresponds to version 3.1, while value 0 by 04 means 3.11. And so logically, 0 by 5 became version 5.0. The sensor network protocol was developed around 2009 to enable battery-powered devices on low bandwidth for wireless networks to benefit from MQTT. The SM protocol allows a gateway device to communicate the full MQTT messages to a broker over a normal TCP-capable network. Message packets from an MQTT SN client are even smaller than MQTT through the use of topic IDs, a 2-byte value that's used to represent the topic name. The wolfMQTT library is organized into 3 distinct components: the client, the packet, and the socket. The client component contains the actual API functions listed here: connect and disconnect, publish, subscribe and unsubscribe, ping, and wait message. The packet component is where you can find all the internal functions for building and parsing the packet structures. And lastly, the socket component is the interface for the lower level networking layer. This could be straight through to TCP, or it can be enabled to use the TLS security courtesy of wolfSSL. You can even pipe the IO through some other peripherals, such as a serial port. Here, I'd like to talk about how wolfMQTT interfaces with wolfSSL to connect using TLS. The net connected API establishes the socket connection before any actual MQTT packets are transmitted. There are 2 parameters related to TLS here: the flag to use TLS and the optional MQTT TLS callback function pointer. A call into the socket component initializes wolfSSL and calls the passed-in TLS callback if it was provided, else the default TLS settings are used. Then the socket receive and send functions are registered with wolfSSL. At this point, all MQTT library IO will be piped through wolfSSL using a secure connection. A bit more about the MQTT TLS callback. It's used to set up application-specific certificates or settings for the TLS connection. Here you could set up OCSP, mutual authentication, specify cryptographic algorithms, or any of the fine-tuning enabled with wolfSSL. You can also set up a verify callback, which can be used to override the client-side failures during the TLS connection. You could also use the callback to do additional verification of the server certificate during the handshake. The verify callback also takes a user customizable context field. In the examples, we pass the MQTT client structure, but it could be any data relevant to your application. So as you can see here, it's very easy to configure the library for various protocols and features that are supported. If you disable TLS support, then the wolfMQTT library can actually be compiled and run completely independent of wolfSSL, but many commercial brokers actually require TLS to be used for authentication and encryption. Debug messages are crucial for figuring out why your application is not quite working right. And that last one there, multi-thread, that allows independent tasks to use a library without internal conflicts. This adds a little bit of overhead, so we made it configurable so as not to bloat the library for size-conscious applications. Building the library, it's very straightforward. As mentioned before, if you want to use TLS, then wolfSSL must be installed first. After cloning from GitHub, you just autogen, configure, and make. That's really it. With a optimized system, it's about 16K for the wolfMQTT library. Great. So now let's talk about the examples. Examples are crucial, but often overlooked part of any successful library. We have taken the time to share as much as possible. The standard MQTT example is very powerful. You can specify a host, port, QoS, topic name, etc. Pretty much everything you need to at least test a broker connection. It's also where the MQTT version 5 specific examples live. The non-blocking client is very popular with microcontroller crowd. The multi-thread example uses a publish task, a subscribe task, and a message wait task, and a ping task to demonstrate that feature of the library. The firmware examples are pretty neat. It has two parts. The first, the FW push, uses wolfSSL to build a hashed and signed firmware image and publish it to the broker. The second part, the FW client, is subscribed to the topic and waiting for the firmware to be published. When it receives the message, the firmware image is unpacked and verified. Whereas the other examples use only a couple of shared utility files, the MQTT simple demo is completely self-contained. It's very straightforward. The sensor network client requires another component besides the broker called a gateway. The gateway handles communication over UDP on the sensor network side and retransmits to and from the broker on the TCP side. Based on support questions, these two brokers probably account for 80% of the wolfMQTT client library usage. The commercial IoT cloud industry has actually been consolidating over the past few years. For instance, IBM's Watson IoT shut down in December 2023, and Google Cloud IoT Core was shut down in August of 2023. So once again, choose your brokers wisely. So those are our examples. They're all neatly contained in the examples folder. There you can also find a couple of utility files that contain code that is used by the examples, but not necessarily needed for in the MQTT library proper. The simple client example executable is roughly 9 kilobytes. So you can see in the output there, the client is connecting to the test.mosquito.org public broker. This is the default for the example. You can also see the TLS is being used to secure the connection. And you'll notice there was an error reported during the TLS verify callback. That's because the CA certificate was intentionally not loaded, causing that error. Then the verify callback that we talked about earlier, that's used to override that failure. Next, you can see the connect, the publish, and subscribe, which are all MQTT functions. And to the end of the client example, if you want to finish it, you just do a Control-C escape sequence, and the example will be unsubscribed and disconnected from the broker. So here's a little about what we accomplished in 2023. So as you can see, we've been quite busy adding features and improving the library. We kind of aim for quarterly releases, though we make some exceptions for critical issues that are reported. Last year was primarily focused on testing, though we did add some new examples, including the Atomic Publish and Subscribe clients, as well as a new OS port for Zephyr and QNX. AWS recently opened the MQTT version 5 broker to general availability. So we updated the example, AWS example, to take advantage of that. And then this is where we're going. So this list consists of things that some folks have asked if we have, and some things that we just think would be neat to have. So we'd like to share the advanced security inherent in wolfSSL with the Mosquito community by providing an open source project port. We're already have a number of other dependencies from other projects. So enabling Mosquito to take advantage of wolfSSL's TLS stack is a natural fit. The port and proof of concept is complete. Next, we're going to work on getting the Mosquito CI tests implemented. So we talked a little about doing a simple broker that would take advantage of the packet library that's already in the client side library. Last year, we added support in the MQTT SN library to secure communication using DTLS 1.2. As a next step, we'd also like to develop a gateway solution to take advantage of wolfSSL's recent DTLS 1.3 implementation. And we're always interested to hear what else we should support. So keep the suggestions coming. And that brings us to the end of the slide. So I'd like to open the floor to questions.
There is a question. Is wolfMQTT HIP certified?
It's certified. Yeah, so the MQTT library itself wouldn't use FIPS certification, but the underlying cryptography that's used for the TLS stack would. So that is something that wolfSSL can provide. We have FIPS 140-2 certificate available now, and our FIPS 140-3 is in process.
Okay. So there's a one person raising the hand, so I will unmute. Yeah, John, I think you can talk now.
Maybe the audio is not working. If you want to type it into the chat, we can certainly answer your question there.
At the meantime, there's another question. Can wolfMQTT SN use DTLS 1.3?
Yeah, so that's something we're actually interested in developing. So DTLS 1.3 was added to wolfSSL library. I think we started on it 2 years ago, and it was finally ratified. And so we've actually got one of the only DTLS 1.3 implementations available. So it's really useful in that it took advantage of some of the things that TLS 1.3 did, and reducing the number of insecure algorithms supported, and then also doing things like reduced handshake time. So that's something we're interested in developing.
Okay. And there's another question. Do you have use cases of wolfMQTT/wolfSSL implementation to share?
Yeah, absolutely. In the examples folder. So we have a number of different simple atomic, just, going through and connecting to like AWS or Azure. Then we also have things like the firmware update examples. So those are all really useful and relevant to other projects.
And there is another question. configuration option mentioned on one of the first slides, are they compile time or runtime or both?
Yeah, sure. So some of them, like the TLS connection, that's actually compile time or runtime. You can enable support for the wolfSSL library using that -- enable TLS configure time option. Then when you actually make a connection, you can just specify whether or not you want to use the TLS security during the connect operation.
There's another question. Does wolfSSL support encrypted client hello?
Yes, it actually does. That was added, I think this past year in 2023. We've actually got some good examples out there also.
There's another question. Does the MQTT firmware update tie into Wolfboot at all?
Yeah, I don't think we've done a proper example of that yet, but that definitely could. And that's something neat. I'm gonna bring that up with the team and see if we can put some examples out there of integrated example of MQTT and wolfboot. That would be neat.
And another question. Oh, okay. So I hope we answered John's question. He asked slide or recording. We will share the slide after the presentation, and the recording will be on YouTube channel. So you can go to YouTube channel to check the recordings. And I do have another question. Can MQTT be used over UDP network?
So MQTT is not really suited for UDP traffic because it needs to have a good answer and response. So that's why it operates over TCP. Now MQTT SN was kind of created to fill that void, basically over UDP networks or stateless connections. So that's where MQTT SN protocol would be used on a UDP network.
And there is another question. Does wolfMQTT support any general apart from cloud provide like MQ or enterprise application?
Yeah, absolutely. So the broker, that's the beauty of MQTT is that since it's a standardized protocol, that kind of abstracts the client's implementation or library that they're using from whatever's on the broker side. So yeah, as long as it complies with the protocol, then you should be able to use our wolfMQTT client library with any broker. I think there was one other question real quick. There was aside from AWS, what are the other public cloud service providers that can use MQTT communication? So there's actually quite a few. We have a good list on our README for the wolfMQTT project that we've tested with. Some of the ones that come to mind are HiveMQ is very popular. Also, Mosquito is another open source project that you would run locally. So yeah.
And then there's another question. How are symmetric keys derived for encrypted client hello?
That's a good question. I'm going to leave that one up to our other engineers. It's kind of outside the scope of the MQTT project, but I'm sure we can get you a good answer if you just want to write into support at wolfSSL or facts at wolfSSL.com.
And if there is no more question, and if you guys still have any question, please email us at wolfSSL. And thank you, Eric, for hosting an informative webinar, and everyone for joining the webinar today. Please don't forget to follow us on Twitter at wolfSSL as well as other social. Thank you again, and see you next week.